Hello and welcome back to the channel. In today's video, we're overclocking the AMD Radeon Graphics integrated in the Ryzen 9 9900X CPU. We overclock it to 3 GHz using AIO cooling and the ASUS ROG Crosshair X870E Hero motherboard. Now, overclocking the integrated graphics doesn't really provide it to a meaningful path to actual performance, but this wouldn't be the SkatterBencher channel if we didn't try and overclock it anyway. In this video, I break down the Radeon graphics tuning process into 4 unique overclocking strategies for beginner and advanced overclockers. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The Radeon graphics integrated in the Ryzen 9000 CPUs is identical to the one integrated in the Ryzen 7000 CPUs. And in fact, we've already overclocked that one in SkatterBencher number 55. The IGP features the somewhat outdated RDNA 2.0 architecture in its smallest form. We get exactly one work group processor. In RDNA 2.0, one work group processor encompasses 2 CUs, as well as 2 ray tracing accelerators. Just like in the Ryzen 7000 CPUs, the Radeon graphics for Ryzen 9000 is clocked at 2.2 GHz out of the box. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications and games to measure performance and ensure system stability. Before we start the overclocking process, of course, we have to check the performance at default settings. The default Precision Boost 2 parameters for the Ryzen 9 9900X and its Radeon graphics are as follows. The Radeon graphics has its own VF curve, operating up to 2.2 GHz at 1.045 volt. Since this guide focuses on IGP performance, I set the UMA frame buffer size to 16 GB, which is half of the total available system memory. UMA is an acronym for Unified Memory Architecture, which is a technology that allows the processor and the integrated graphics to share the memory. The UMA frame buffer is the portion of the system memory that's exclusively reserved for the integrated graphics. The rest of the system memory can be accessed by both IP. So usually you don't need to adjust the UMA frame buffer, but it can help for certain applications. Here's the benchmark performance at stock. Here's the AI performance at stock. Here's the game performance at stock. And here's the memory performance at stock. For the stress test part of the guide, I still rely on OCCT as I usually do, but rather than picking one specific workload, I used its combination function to run both 3D adaptive and VRAM workload at the same time. The reason is simple. I want to stress the GPU and dedicated portion of the DDR5 memory at the same time. When running the OCCT 3D adaptive and VRAM combined stress test, the average GPU effective clock is 2223 MHz with 1.272 volts. The average GPU temperature is 47.6 degrees Celsius, and the average GPU core power is 29.2 watts. Of course, we can override the power consumption limits by enabling Precision Boost Overdrive, and that's exactly what we'll do in our very first overclocking strategy. However, before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply take advantage of enabling AMD Precision Boost Overdrive 2 and AMD EXPO. Similar to the Ryzen CPU cores, the AMD Radeon graphics integrated in Ryzen CPUs is also subject to the Precision Boost 2 governors. That means that the performance limiters of Precision Boost can also constrain the integrated graphics performance. Now, Precision Boost 2 has performance limiters that go across all the IP blocks in the CPU, as well as some limiters that are specific to the CPU cores and specific to the integrated graphics. The Precision Boost Overdrive 2 toolkit for Radeon graphics includes the overclocking knobs from Zen Plus, PPT, TDC, and EDC, and Zen 3 Curve Optimizer. Unfortunately, there's no graphics F-Max boost override like we have on Ryzen 8000G APUs. There are essentially 3 levels of Precision Boost Overdrive. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Since the integrated graphics use very little power, we don't expect enabling PBO to have a major impact on system performance. EXPO stands for Extended Profiles for Overclocking, and it's an AMD technology that enables ubiquitous memory overclocking on DDR5 platforms. EXPO allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting, so it saves you from a lot of manual configuration. Upon entering the BIOS, we rerun the benchmarks and check the performance increase compared to the default operation. Enabling higher power limits doesn't really affect Radeon Graphics since it operates well below the Precision Boost 2 performance limits. But as we often see with integrated graphics, enabling higher memory performance makes a big impact on benchmark performance. The geomean performance speedup is plus 11.86%, and we get a maximum benchmark speedup of plus 17.85% in Age of Mythology. When running the OCCT 3D Adaptive and VRAM combined stress test, the average GPU effective clock is 2221 MHz with 1.279 volts. The average GPU temperature is 50.5 degrees Celsius, and the average GPU core power is 34.6 watts. Attentive viewers will have raised their eyebrows twice by now because of the reported operating voltage in the OCCT stress test. Both at stock and in OC strategy number 2, I state that the operating voltage is over 1.27 volt. However, the Radeon Graphics VF curve clearly shows that 2.2 GHz should run at about 1.05 volts. So why do I say 1.27 volt? Well, it's because of the Granite Ridge voltage topology. The Ryzen 9000 voltage topology relies on a combination of internal and external power supply to generate the processor voltages. There are 4 primary power supplies from the motherboard VRM to the processor. Even though the integrated graphics IP block is located on the I/O die with the rest of the SoC IP, it's not powered by the VDDCR SoC voltage rail, but instead gets its power from the VDDCR voltage rail. The VDDCR voltage rail provides external power for 3 internal voltage regulators: VDDCR CPU, VDDCR VDDM, and VDDCR graphics. VDDCR GFX provides the voltage for the integrated graphics. The voltage rail can work in either DLDO or bypass mode, but on Granite Ridge, it's always in bypass mode. Crucially, that means the voltage is always equal to the VDDCR external voltage. The VDDCR voltage rail is directly controlled by the CPU SMU using an SVI3 interface. The voltage selected or programmed is the highest among the requests of its dependents. In this case, that's the 12 CPU cores and the integrated graphics. And that's why the integrated graphics gets more voltage than needed. It's the CPU cores requesting a higher voltage from the VDDCR voltage rail. Of course, it would be great if the integrated graphics could run in DLDO mode rather than bypass mode, or even better, if the integrated graphics had its own voltage rail entirely. The next question is how much the forced elevated voltage impacts power consumption. The easy way to check this is by setting a negative frequency boost override for the CPU cores. This ensures the highest voltage requested by the CPU cores will be much lower. I ran the same OCCT combined stress test as OC strategy number 1, but with a minus 1000 Fmax for the CPU cores. That results in 200 millivolt lower operating voltage, almost 3 degrees Celsius lower operating temperature, and almost half the GPU core power usage. While this tells us a more genuine story about iGPU performance and power consumption, it's not something that you would normally do. You wouldn't downclock your CPU cores to lower the iGPU power consumption. So therefore, for the rest of this guide, I will stick with the default CPU frequency. In our second overclocking strategy, we try to increase the graphics clock as high as possible. But before we get into that, let's first have a look at the clocking topology of a Ryzen 9000 CPU. The graphics frequency or graphics clock is derived from a 100 MHz internal or external reference clock input. The reference clock is multiplied by a graphics clock ratio, which you can configure in the BIOS. Configuring the value in the BIOS sets the graphics clock max override and forces the GPU to operate at that frequency. The Radeon Graphics also have their own voltage frequency curve. At 2.2 GHz, we need about 1.045 volt. The lower voltage limit is 720 mV and the upper voltage limit is 1.25 volt. We hit this limit at about 2.5 GHz. Any frequency higher than 2.5 GHz is also restricted to the same 1.25 volt. The voltage frequency curve is really more of an abstraction than a set of programmed values. That's because of AMD's adaptive voltage frequency scaling technology. Since 2015 and the Carrizo APU, AMD utilizes adaptive voltage frequency scaling or AVFS. This technology relies on replica paths to the circuit that serve no other purpose than to assess whether the circuit is stable. The AVFS technology then infers the stability of the real paths using sampling statistics. Despite having these advanced clocking technologies like AVFS, AMD cannot predict what will happen in the real world. Sometimes transient conditions, going from idle to load or from load to idle, are so impactful that the CPU might crash in a real-world scenario. Fortunately, AMD also has a voltage adaptive operation technology, commonly known as clock stretching. The technology consists of two circuits. One circuit serves as a configurable droop detector, and the second circuit functions as a configurable digital frequency synthesizer. The idea is simple. Since the operating frequency is tied directly to the voltage, if a voltage droop is detected, the effective clock frequency gets lowered to ensure continuous operation rather than having a system crash. The real-world impact of voltage adaptive operation is that the effective clock can differ from the set target clock. AMD graphics heavily rely on this voltage adaptive operation to continuously maximize the frequency for a given voltage level. And so what we'll see in the real world is that heavier workloads, where the voltage will droop a little bit lower, will increase the gap between the set target clock and the effective clock frequency. If the theory feels overwhelming, then I have great news. Actually doing the overclocking is much more simpler. In fact, it's just a matter of running up the target clock until you see signs of instability. I found that the earliest sign of instability is getting artifacts on desktop. I got these around 2.9 GHz, so I settled for a GPU clock frequency of 2.8 GHz. Upon entering the BIOS, we reran the benchmarks and checked the performance increase compared to the default operation. With a GPU frequency increase of about 27%, we'll obviously get higher performance across our entire benchmark suite. It's interesting to see the memtest of Vulkan write and checked bandwidth also scale significantly with increased GPU frequency. The geomean performance speedup over stock is plus 35.21%, and we get a maximum benchmark speedup of plus 42.86% in returnal. When running the OCCT 3D adaptive and VRAM combined stress test, the average GPU effective clock is 2812 MHz with 1.286 volts. The average GPU temperature is 53.4 degrees Celsius. The average GPU core power is 41.4 watts. I want to take a quick moment to highlight the impact of increasing the GPU frequency and therefore its associated voltage. As I already established in a previous segment, the CPU cores and the integrated graphics share the same voltage rail. That means that if we increase the graphics voltage, it might also increase the CPU core voltage. To illustrate this point, I ran the same configuration from SkatterBencher number 92, OC strategy number 1, but with the integrated graphics enabled and running a light workload. This is the same system, same hardware. At first, nothing too spectacular. The package power increases by about 30 watts and the temperature remains at 95 degrees Celsius. But the devil is in the details because we can see the average VDDCR VDD voltage is 100 millivolt higher due to the integrated graphics. That increase in voltage triggers a number of precision boost performance limiters, and we find the CPU cores running at 1.2 GHz lower frequency. So be aware that running overclocked integrated graphics may significantly affect CPU performance in high load scenarios. Side note, the limiting factor in this particular test is actually the operating temperature. So maybe I'll have a look with liquid nitrogen and see how far we can push the power consumption. In our third overclocking strategy, we delve into tuning the memory subsystem. Now, on AMD Ryzen CPUs, the memory subsystem consists of three major parts: the Infinity Fabric, the memory controllers, and the system memory. First generation Ryzen overclockers know that these parts used to be tightly coupled together, but on modern Ryzen processors like the Ryzen 9 9900X, we can tune them independently. The fabric frequency, or F-clock, is generated by the SoC PLL, derived from a 100 MHz reference clock input. The reference clock is multiplied by the F-clock ratio, which you can configure in the BIOS. The standard operating frequency of the Infinity Fabric is 1800 MHz, but on many motherboards you'll find it runs at 2 GHz when Precision Boost Overdrive is enabled. Tuning the Infinity Fabric probably has a minimal impact on graphics performance because the graphics IP block is on the I/O die, just like the memory controllers. That said, it doesn't seem there's that much overclocking headroom beyond 2 GHz. I managed to set 2.2 GHz for this overclocking strategy, however anything higher couldn't boot reliably, not even with voltage adjustments. Speaking of the voltage, the Infinity Fabric voltage is provided by the VDDG voltage supply, derived via an integrated voltage regulator from the VDDCR miscellaneous voltage rail. There's a total of 4 VDDG voltage rails available for manual adjustment. AMD Granite Ridge has two DDR5 Unified Memory Controllers, or UMC in short, and each provides two 32-bit memory channels. The memory controllers are located in the I/O die and are identical to the memory controllers on Ryzen 7000 Raphael processors. The Unified Memory Controller frequency, or UClock, is derived from the UMC clock, one of the SoC PLLs. The UMC clock is driven by a 100 MHz reference clock derived from either an internal or external clock generator. The memory controller frequency is tied directly to the system memory frequency. It can run either at the same or half its frequency. At default, the memory controller runs at the same frequency as the system memory at 2400 MHz. However, we find that when enabling EXPO, the motherboard auto rules will drop the memory controller frequency to half the memory frequency. We could easily force the memory controller to run at the same frequency as the system memory by setting uclock div1 mode to uclock equals memclock. However, that's only possible if we run the memory at around DDR5 6000. The VDDCR SoC voltage rail provides the external power for multiple internal voltage regulators on the SoC for various IP blocks, including the memory controller. The VDD-IO mem voltage is related as it provides the external power for the VDD-P DDR5 bus signaling. The final piece of the puzzle for optimizing the memory subsystem is of course tuning the memory timings. And for that, I rely in part on ASUS memory presets. ASUS memory presets is an ASUS overclocking technology that provides us with a number of presets for specific memory ICs. Typically, it will adjust the memory timings and the voltage. The ROG Crosshair X870E Hero motherboard sports 14 memory profiles for a variety of memory ICs and configurations. Since we're interested in simply adjusting the memory timings, we can try the Hynix 7600 MHz 1.45V 2x16GB single rank preset. Unfortunately, unlike with previous overclocking guides, I had to adjust quite a lot of memory timings to make the memory pass our target of 1 hour of OCCT stress testing. Here's the final optimized memory timings for this memory kit. After the memory subsystem tuning, our ADAS64 performance improved quite significantly. We got about plus 40% extra bandwidth and 20% lower latency by enabling EXPO. The memory tuning then added another 20% improvement on top of that. The memtest Vulkan performance also improves another 30 to 40%, though the biggest gains come from overclocking the GPU. Upon entering the BIOS, we reran the benchmarks and checked the performance increase compared to the default operation. As we've seen with other integrated graphics, tuning the memory timings can have a significant impact on performance, especially in workloads which are memory dependent like games and AI workloads. The geomean performance speedup over stock is plus 46.01%, and we get a maximum benchmark speedup of plus 57.14% in Returnal. When running the OCCT 3D adaptive and VRAM combined stress test, the average GPU effective clock is 2814 MHz with 1.285 volts. The average GPU temperature is 54.1 degrees Celsius. The average GPU core power is 43.6 watts. In our final overclocking strategy, we do everything we can to squeeze even more frequency out of our GPU, which includes overvolting using the graphics curve optimizer. Curve optimizer is one of the most important tools in a Ryzen overclocker's toolbox. It's most commonly known for its CPU core undervolting capability, but for AMD Ryzen CPUs, it's also available for the integrated graphics. To explain how it works, let's start with the basics, the voltage frequency curve. Here's the default voltage frequency curve of the Radeon Graphics. We can immediately make a simple and redundant observation. The higher the frequency, the higher the voltage. For example, for 2 GHz we only need 0.935 volt, but for 2.5 GHz we need 1.25 volt. If we set a negative curve optimizer, we can shift the entire voltage frequency curve along the voltage axis, and suddenly we need a lot less voltage for every operating frequency. For example, at default for 2.5 GHz we needed 1.25 volt, but with a minus 15 curve optimizer we only need 1.18 volt. Similarly, a positive curve optimizer will make us use more voltage for every operating frequency. We can use this tool to try and stabilize higher frequencies at 1.25 volt. In my case, I set the GPU frequency to 3 GHz and a plus 20 curve optimizer. That yields an effective clock frequency of over 2.9 GHz in our OCCT stress test. Now, some of you might be thinking, Peter, why are you not controlling the VDDCR voltage directly? It's a solid idea because it would give us direct control over the graphics voltage. Unfortunately, turns out that additional voltage doesn't really give us additional frequency. We run into the same artifacts like we do at 3 gigahertz. Upon entering the BIOS, we reran the benchmarks and checked the performance increase compared to the default operation. By marginally increasing the effective clock frequency, we get a minor bump in performance in most of our benchmark workloads and games. The geomean performance speedup over stock is plus 49.85%, and we get a maximum benchmark speedup of plus 58.08% in Age of Mythology. When running the OCCT 3D Adaptive and VRAM combined stress test, the average GPU effective clock is 2915 MHz with 1.269 volts. The average GPU temperature is 53.8 degrees Celsius, and the average GPU core power is 37.9 watts. Alright, let's wrap this up. I'll be the first to admit that overclocking the Radeon graphics integrated in the Ryzen 9000 CPUs is a bit of an academic exercise. Yes, it's possible. Yes, there's quite a bit of frequency headroom. And yes, the performance uplift is quite impressive. But double of nothing is still pretty much nothing. It was interesting, however, to see the impact of this shared voltage rail between the CPU cores and the integrated graphics. In very specific niche scenarios, increasing the graphics frequency by 300 megahertz and therefore increasing its associated voltage actually reduces the frequency boost of the CPU cores by more than 1 gigahertz. So maybe it's worth contemplating to give the integrated graphics, however tiny it may be, its own dedicated voltage rail. At least provide the option on high-end motherboards. And while we're at it, also give it an upgrade to RDNA 4. That will give us a little bit more performance too. Anyway, that's it for this video. I thank you for watching, the patrons and the YouTube members for their continued support. If you have any questions or comments, feel free to drop them in the comment section below. As per usual, I'll also put up a written version of this video up on my blog so you can read through all of my performance results and BIOS settings. And that's it. Have a good one.